Hydraulic Engineering for the 30th of January 2014. Today is a Thursday, and this is class number 6 of the semester. We'll begin with a couple of announcements. First of all, this class is being posted online. We are not physically present in the classroom right now, and so if you have any questions from today's lecture, since it's a recorded lecture and you don't have the chance to interact with me live, please feel free to send me an email. Although I'm out of town for today, I'm going to be responding to email as quickly as I can, so please let me know if you have questions, and of course I'll have office hours when I return and would be happy to meet with you on Monday as well, even though I don't have office hours that day. Also, homework number 3, which is 2 problems from Chapter 8, is going to be due on Tuesday, February 4th, and so that'll be the next time that we meet in person. Both of those questions are related to the 3 reservoirs type problem that we're going to be talking about today. Just the fact that you have 2 problems shouldn't be taken to mean that these are overwhelmingly hard, but it's a little bit unfamiliar, and I didn't want to give you too many problems all at once, and so those 2 questions are going to be due on Tuesday, and so the example that we work through today, I think, will give you a pretty clear idea on how both of those can be solved, and thankfully, because those are both heavy iteration, they can be solved using Excel. Just a note about today's lecture is it's previously recorded from last semester, from the spring 2013, and so you may hear a few students asking questions, and I'll be pausing the recording at certain times when I was working through the demonstration with them. I've reviewed the recording, and I haven't made any changes to my notes from last semester to this semester, so I think it will be a fully valid way to communicate the information to you. I don't think there is anything that isn't going to apply. But again, if you have any uncertainties or questions, please send me an email.
So here is the famous 3 reservoir problem. Essentially, we've got 3 reservoirs connected together, and just by inspection, we know that water should flow out of reservoir A. Since it's the highest, water is going to drain from a location of high energy towards a location of low energy. And we should know that, of course, water is going to flow into reservoir C since it's at the lowest elevation. But then reservoir B is the one that's really uncertain, that we don't know if the flow will enter reservoir B or if it'll exit reservoir B. And so what complicates our analysis of this is that energy loss is a function of velocity. And we don't necessarily know how quickly the water is flowing through these pipes. We may know direction, but we don't know the rate that water is flowing. And so since we don't know the rate that water is flowing through each of the pipes, we don't know the head at the junction. This location D is actually where we're going to try and solve the whole conundrum. And what we're going to be using as our tool to solve the problem is the continuity equation. Remember that flow in has to equal flow out at an enclosed junction like this. This junction is just a conduit where the 3 pipes come together, and there's no reservoir at D where water levels could raise or lower. It's just however much comes into D has to go out. And that's what we're going to be using as the tool to answer the question, what direction is the water flowing, and what are the flow rates through each of the pipes. So any questions so far? All right, water flows out of the high reservoir into the low. Middle reservoir, we're not certain about. What we know is that there's going to be energy loss through each of the pipes. And so remember, we said that location D is sort of our key to answering all of these questions. So let's say that there's a certain amount of energy at C, and we know how much because the elevation of the water surface is known. Is there more energy at D or less energy at D if the water is going in the direction that's shown on screen there? So the water is flowing from D towards C. And so what can we say about the head, or the energy at D, in terms of how much energy there is at the reservoir C? More or less? Why do you say there's more?
The elevation's higher, it's flowing that way.
Okay. Even if the elevation wasn't higher, it still could be more energy, because remember that the hydraulic grade line is independent of physical location. So what really is the defining, like why the energy at D is greater is just by definition, water flows from high energy to low energy. And so if the water is going from D towards C, the head at D has to be greater than the head at C. And so we're going to try and write the energy equation between 2 points in terms of the direction of flow. So we're going to be using this head loss term to find out how much energy difference there is between 2 points. But the problem in applying that is that we don't know the velocity through the pipe. So for example, if I said the head at D is the head at C plus the head loss between D and C. So that just means that the amount of energy that there is at D, there's however much at C plus the losses that occurred in the pipe. Or another way of saying it is the head at C is how much head there is at D minus the head loss between D to C. I mean, that's clear enough, but the problem is our formula for calculating head loss, the Darcy-Weisbach equation, we have to know the velocity in order to calculate the head loss. And so we're going to have to write things in terms of some guess flow rate. So we're going to have a whole series of interdependent guesses. And we'll know that finally we've got the right guess of things when we find that the flow out of D equals the flow in. That's our indicator. All right. So here's the iterative solution method. And by the way, there isn't going to be some easy explicit method after I show you this implicit approach. Remember, with the whole what's the right diameter problem, then all of a sudden, well, there is an explicit equation. It's an ugly one. But in this case, there won't be some easy way of doing it. We have to guess how much head there is at D. We'll just pick some initial starting value for how much energy is there. One common approach is to just say the amount of energy at D is equal to the elevation of the water surface at B. But you don't necessarily always want to make that assumption. It doesn't have to be that. But sometimes you just say, well, the amount of energy at D is between A and C. It wouldn't be more energy than A, and it wouldn't be less energy than C. So we have some guess value. Now, we're going to set up equations for head loss in terms of F and V. And so this formula here, if we wanted to find the head at D, we'd say the head at D is head at C. And head at C will be known because what will be given in a problem like this is the water surface elevations. And so we would get this, it's known from the water surface elevation. So what I'm saying here in step 2 is that the head loss equation, we're going to have H sub F, just the friction losses between C and D, and we're going to write it in terms of the length of the pipe between them will be known, the diameter will be known, but what will be unknown is F and V. So we'll write the head loss equation, and we'll leave F and V as variables. And then we're going to have to assume a value for F the first time around. The second time we go through this iteration, what we'll do is we'll use a previously calculated value of F. And so you can either use the Moody Diagram to find an F value, or you can use the Jane equation to find an F value. But we initially aren't going to know the velocity, remember. And so maybe one smart technique for guessing what's the F value is just, in this first estimation, use the relative roughness. Assume, well, maybe we're in the fully turbulent zone to begin with. And that would give you a starting point for what F to use. So once you know F, and you know how much head loss there has to be, if you've assumed some certain D, then that'll allow you to find the velocity. Then for whatever velocity corresponds to the location that we've guessed for the head at D, and remember we've also guessed what the F value is, that leads to some velocity. We use that velocity to calculate the Reynolds number. With the new Reynolds number, well, with the Reynolds number that we found, we find a new F value and a new velocity, kind of like tuning in our F value, getting a little bit closer. And then finally, with this updated velocity, we find out what's the flow rate through each of the pipes. We check the continuity, and if the flow rate out of the junction is greater than the flow rate in, what that means is that the guess is of how much head is here is too high. Because if the amount of head at D is too high, that's going to be sending water really fast towards C. There would be a big driving force. Think about there's tons of pressure at D that would shoot water towards C really quickly, but then there wouldn't be much of a driving force taking water from A and from B towards that junction. So that's what this logic is based on, is that if the flow rate out is bigger than the flow rate in, that means that your guess of the amount of energy at D is too high. On the other hand, if I didn't change the signs there, correct this in your notes. If Q out is less than Q in, then that means that you have to raise the guess of the head at D. So D is too low, then that means you're going to have a lot of water flowing into D because it's a really low energy location and not very much of a driving force from D towards C. So when you've got just the right estimate of where D is, and you also will, having gone through this a couple of times, have a correct estimate for the F value and for the velocity, then you know you're finished. You've reached the correct solution. You've reached convergence when the continuity equation is satisfied. Okay. Any questions about that? Well, we're going to apply that method to this problem today. And so you've got computers there, and what I'm going to do is I'm going to set up a structure of a spreadsheet, just showing you what columns to create, what rows initially to establish, and then we're going to go through the process of actually solving the problem together. And so before we get into Excel, let's just take a look at what we know. We know that the highest reservoir has an elevation of 120 feet, middle reservoir 110, lower reservoir 70 feet. Got two pipes that are cast iron, one that's galvanized. So we're going to have to look up two different K sub S values, two different equivalent sand roughnesses, that is to say. We've got the lengths and the diameters. And so what aren't we going to know? We don't know how much energy there is at D. So we're going to have that guess value that we start with. We don't know what velocity the water will be through the pipes. And so that means we don't yet know what the F values are going to be. And so we're going to set it up. So just as some preliminaries, let's gather some info and put it on the board. We've got cast iron. One of the pipes is 12 inches. And the other pipe is 8 inches. And then we've got galvanized iron. Okay, let's go to the value of equivalent sand roughnesses. See if we can track that down. All right, so cast iron in terms of feet, cast iron, okay, so 0.00085. And that's feet. So I'm going to multiply it by 12, and that'll give me inches. So I want to find, the reason why I'm doing this is I'm going to find the relative ratio so that I can have in mind what's my first guess of F. Okay, so same thing here. I guess since it's times 12 inches and divided by 12, our K sub S to D for this first pipe, for the 8-inch pipe, will be this. And the K sub S to D for the 12-inch pipe is just going to be 0.00085. galvanized iron has a K sub S of 0.0005, and our diameter for the galvanized iron pipe, let's go back to that, that's an 8-inch pipe. So times 12. All right, so someone got a calculator that can tell us what's our relative roughness for this 8-inch pipe. In other words, what's 0.00085 times 12 divided by 8?
1.275 times 10 to the negative third.
All right, so this is what we're going to use as our relative roughness. And how about the galvanized iron?
That looks like 7.5 times 10 to the negative fourth.
All right, so we've got the relative roughness, and my suggestion was what we could do is we could take a look at the Moody diagram and say as a guess that we're in the fully turbulent range. And so let's look up for 0.13 times 10 to the minus third. Boy, that's really hard to see. 1, 2, 3. Okay, so going over here, that would be a net value of 0.021 is what we'll use for the 8-inch pipe as our initial guess. 0.005. Okay, so 0.085 would probably use just 0.02 for our first one on the 12-inch pipe, and then the galvanized iron, 7.5 times 10 minus fourth. That would be a little bit lower. We use 0.019. All right. So we'll just sort of keep that in the back of our head as these initial values of F that we're going to use in step 3 of this process. All right, so start up Excel, and these are the columns that you should have in Excel. Go ahead and start typing in the columns. One is going to be naming the line, material, the K sub S. Let me make that a little bit bigger for you. These column names. I've got some equations on mine that you don't necessarily have to type those equations in. I paste them just for convenience when I'm setting up the equations. But create columns that look like this. I'm going to pause this momentarily. Okay, so area pi d squared divided by 4 to calculate the area. Our guess value of the head at D, just to see how things go, I'm going to pick a different value than I normally pick. Hopefully it doesn't lead to pandemonium. Let's just say, what if it's 100 feet? And so I'm guessing at this point that there's 100 feet of head at location D. And the range of possible values seems like it'll be less than 120 and more than 70. So if there's 100 feet of head at D, then how much head loss is there going to be through pipe, each of the pipes, through pipe DC, AC, and BC? The formula for that is just going to be the elevation of its head. And so in the case of pipe AD, it's 110. So it'd be 110 minus however much is here. That means 10 feet of head loss through there. If it's BD, that's at 120, so 120 minus the guess. And then DC, it is going to be 100 minus, well, not 100, okay. The reference to 100 minus 70. So all of the values, the head loss values themselves are positive, but you'll notice that I switched the direction of what was subtracted first. When the flow was going towards junction D, I had the head at D minus the initial value, and the other way around for DC, because in DC I assume that flow is going from D towards C. So we'll put in these guess F values that we first came up with. The smaller of the cast iron pipes was the one where we said we'd use 0.021 for our guess F value, 0.02 for the next one, and for the galvanized iron pipe, 0.019. And that's sort of what we picked, assuming that we were in the fully turbulent range and looking it up off of the Moody diagram in a real quick way. Okay, so what will be the velocity if that is the F value? You can see that here on screen I've rearranged the Darcy-Weisbach equation to solve for velocity. So H sub F is known. That's this column that we defined here. H sub F is known, the diameter is known, G is a constant, F I've just guessed, and the pipe length is also given in the problem statement. So for each of these I'm going to calculate if that's where the head at D is, and if that's the F value, what would be the velocity. So square root, actually let me zoom in a little bit. Square root of H sub F times the diameter times 2 times G, 32.2 since we're in traditional units, divided by F, which is I-26, divided by the length. Okay, I'll pause here for a second and see, does anybody have questions with what we've gone over so far? No questions so far. Okay, so I can just drag that formula down and calculate the velocity for each of the other pipes as well. All right. So if that's the velocity, now I can find the Reynolds number. Have I got the Reynolds number equation on here? Well, I'll put it, the only thing I need to double check on is the kinematic viscosity of water in these traditional units. All right, the kinematic viscosity of water that we're going to use, let me reference it right here. Kinematic viscosity of water, and the units are going to be feet squared per second. It is 1.138 E negative 5. Okay, so when I calculate the Reynolds number here, that's going to be the velocity of the water times the diameter divided by the kinematic viscosity. And I'm going to anchor that reference to kinematic viscosity. Drag down the Reynolds number. Do I need to pause? Should I wait a second?
You got your velocity, so.
Velocity. The formula for that. Yep. So square root the head loss times diameter times 2G divided by F divided by L.
You can type it in E0. Yeah.
You all right? Fine. All right. Okay, so now if we know the Reynolds number, we're going to calculate F, this time using the Jane equation. So 1.325 divided by ln of K sub S divided by 3.7 divided by D plus 5.74 divided by Reynolds number K26. I can't click on it because my stupid formula is in the way. To the 0.9 power because it's centered. Close that. Now we want to square it. Double check, make sure there's no errors there. So our first guess wasn't so bad, getting a slightly different F value. I'm going to change the way it looks into number format. I can drag it down.
Could you display that equation again?
Yep. I wish there was some way to make it bigger up here, but I don't know of a way.
By the way,
Yeah.
I have to change that. I got a constantly velocity. Okay, velocity times diameter divided by the kinematic viscosity, which is 1.14 times 10 to the minus.
Anybody else have questions?
All right.
Kinematic viscosity?
I'm just gonna work.
What's that?
Let's go.
Kinematic viscosity, remember, is just, we're going to have Reynolds number is velocity, diameter, divided by kinematic viscosity, and in traditional units, that's 1.138 times 10 to the minus 5 feet squared per second.
Okay. That's great.
Okay, so we're going to now find a new velocity using the same equation as before, still using the modified Darcy-Weisbach equation. Okay, so again, velocity is square root of h sub f. Hold on a minute. Yeah, we use the same h sub f. Okay, so square root of h sub f times d times 2 times 32.2 divided by f. In this case, it's L 26 divided by the length. Our velocities didn't change all that much, but they changed a little. Okay, by flow direction, what we want to do is identify if the flow is going into the junction or out of the junction in each of these rows. And so in the first row, it was AD, and what we assumed is that there was more energy at A than at the junction. And so the flow is going in to the junction through that pipe. The flow is going into the junction through pipe BD, and through pipe DC, the flow is going out of the junction. Okay. Any questions? Okay, so our flow rate is going to be easy to calculate. It's just the velocity times the area. And then for error, what we want to do is at the bottom here, we want to have all of the ins minus all of the out. Let's go back to our criteria and see what we're trying to judge. If out is bigger than in, then we need to lower our guess. If out is less than in, we need to raise the guess. And so what I'm going to try and do is I'm going to have in minus, let's see, if we have out minus in and it's positive, that means we need to lower the guess. So I'm going to have out minus in equals the out minus both of the ins. So in other words, what I'm doing here for error, I'm saying Q out minus Q in. So we can see in this case that there's more flow going in than is going out. More flow in than going out. So what does that mean? In is bigger than out. That means we need to raise the guess of H sub D. So let's sort of step back from the spreadsheet and try and think in physical terms what this first iteration has told us. The way that we're solving this problem is we're trying to guess how much energy there is at D. Because if we know how much energy there is at D, then we can calculate what the flow rate is through each of the pipes. But our guess was wrong, and our guess was too low. And the way that we know that this guess of 100 feet is too low is because when we guessed it, it told us that the flow rates that are consequential of that energy level told us that the flow out would only be 4 cubic feet, but it looks like the flow in is about 8 cubic feet. And so we're off by 4 cubic feet per second. So the conclusion here is out is less than in, must raise guess of HD. All right, so we're going to do this again. This was iteration 1. Now in iteration 2, I'm going to just copy all of the rows, and then I'm going to go in and fine-tune some of the equations. But just to get things started, I'm going to select all of these rows. Then I'm going to copy and paste. First of all, I'm going to change the name of it so that it says iteration 2. Well, what's going to be different in iteration 2? Well, I want to guess a different value of h sub d, and so I'm going to say 105. I decided in the last one that I needed to raise my guess of HD. This doesn't tell me how much, but it tells me I need to raise my guess. I'm also going to change, instead of typing in 100, I'm going to just have it reference this other cell. That saves me from having to type in 105. So the guess of the head is for all of those. Now, if it's at 105, then the water flows are still towards D for both of these upper reservoirs and into C from D. And so, like, if I had guessed that if I picked my new H sub D was 111, then that would change the direction of flow from D to A. And that's a really important point, because in your homework, you're not going to necessarily know if your first guess is too low or too high. Like this middle flow rate, the middle reservoir will be a little uncertain. And so what I'm telling you right now is important, that if I guessed a head at D that's above this elevation of water, then that changes the flow direction. It starts sending water into A if the head at D is greater than the elevation at A. And so then that would adjust these head loss formulas. Let's see if these are still accurate. The head loss through the pipe, it seems like it pasted the value but not the formulas. Huh. Okay, it didn't do a very smart paste. So I'm going to copy this, Control C, Control V. Now it pasted the formulas instead of just pasting the values. I guess maybe the default functionality is to paste the values. What I wanted is I wanted to paste the formulas. Okay, so does this make sense? That if the head at D is 105, there's going to be 5 feet of head loss through this first pipe, AD? Yes. From 110 to 105, there will be 5 feet of loss. From 120 to 105, there will be 15. And there's 35, because now if the head at D is 105, I'm 35 feet above 70. And so these head losses make sense. Instead of just some random guess of F, what I'm going to use as my guess value of F here is I'm just going to have it look up what the previous value was. And so instead of typing in a value, I'm going to have it actually reference the previous one. So equals, and I'm going up here and just having it choose the most recent version of F that it found in the previous step. All right. And in fact, I could do even better than that. I suppose I could just, well, we'll have it do that for now. Okay, so we have, this is finding the velocity based on the same process as before. The Reynolds number is doing the same thing, V times diameter divided by kinematic viscosity. It's looking up here at the kinematic viscosity definition that I put in. The F value here is using the Jane equation. So you'll notice that the F value didn't really change very much, did it? F value seems to be converging nicely. That means we're getting closer to the correct value of the head at D. It's found new velocities. And so we'll take a look at, is this still into the junction? Yes. That is still in, that flow rate is still into the junction. That flow rate is out of the junction. So now we're going to do out minus in. So this one is out, minus in, minus in. Okay, so what's the conclusion this time? Which is what? What do we need to do to our guess at D? Should the next guess of D be greater than 105 or less than 105?
Greater.
Greater. We need to raise it even more. But we're getting closer. You know, the error is wrong. So out still less than in, must raise guess of HD. Okay, so this time I'm going to copy everything. Control C. Where to put it? I'm going to put it right here. Control V. No. Okay, selecting just Control C, Control V. Okay, iteration 3. So let's say 109. It calculates all the head losses, F values, velocity. Now at 109, the flow directions are still as I had anticipated. I haven't gone above the water surface at A, and so the flow rate is still going from A towards D. So all the flow direction guesses are correct. There's really nothing we need to do. The F value is referencing the most recent value of F from the previous iteration, which is fine. These F values are calculating an improved F based on the new Reynolds number it's picking up. So let's find out the flow balance. The out minus both of the ins. All right, 106 negative. So still, it needs to go higher. At this point, we can just sort of play around with our guess value here until we notice that that goes to 0. So what about 109.1? 109.2? Is there a faster way than doing this? We could do goal seek, right? Let's see if we try firing up goal seek. Our goal is that we want this to be equal to 0 by changing that. Let's see if this works. It do. Okay, there's our answer. That's the head at D that is going to make everything correct. That's the head that's going to make the F value such that the flow rates are going to equal. Maybe just to double check that this is a nice tight convergence, what I'll do is I'll copy it again and paste it. And the reason why is I'd like for the F value to not change at all, even within a step. So here it's looking at the previous one. Here it's converging it a little. So if we do goal seek again here, we want that to be equal to 0 by changing this. Okay, it changed it by a very minuscule amount. All right, so that is the 3 reservoir problem. The only complication beyond which I haven't shown you, but I've mentioned it, is that if we had to go above this middle elevation, then what that does is it makes it so that when we calculate the head loss, that it becomes, you switch the two things in this cell. The flow direction is what governs the H sub F formula, and so then it would be an out, and so you'd be subtracting different things. But I think you'll figure that out in the process of the homework. That concludes this demonstration of the 3 reservoirs problem.